Assalamualaikum and good day. I bid to my lecturer, Dr. Maman, and the graduate assistants, Rafael and Paris. I'm Dania from Group 2, and today my colleague Emir and I will be presenting on the pressure profile. So, what is a pressure profile actually? So, pressure profile is the illustration of change in the pressure with depth. And as we can see on the figure on the right, which is showing us a pressure profile, it displays the hydrostatic pressure, the under pressure, over pressure, and also the overburden stress. And this pressure profile is important to us because it identifies the abnormal pressure zones in the formation. In the pressure profile, we can see three types of pressures, which is the hydrostatic pressure, the overpressure, and also the underpressure. So, hydrostatic pressure, or also known as the normal pore pressure, is the formation fluid pressure, which extends from the surface to the depth of our interest, whereas the abnormal pore pressure is the lower or higher pore pressure than the hydrostatic pressure, and this includes the overpressure and also the underpressure. The overpressure, or also known as the excess pressure, is a pore pressure that is greater than the hydrostatic pressure. Meanwhile, the underpressure, or also known as the subnormal pressure, is the pore pressure which is lesser than the hydrostatic pressure. Moving on to the abnormal pore pressure. So the abnormal pore pressure exists in many of the geological basins and also the sedimentary formations around the world. And it is important for us to predict the abnormal pore pressure in the formations. This is because it will help in the drilling planning and operations, as well as to avoid the drilling incidents such as the kicks and also blowouts, and lastly to prevent geological hazards and disasters such as the weaknesses in the faults and also the mud volcanoes. And the solution to these hazards and disasters are to analyze the origin and the mechanism of these abnormal pore pressures. Next is the mechanism of abnormal pore pressure. According to Mochet in 1989, there are 7 mechanisms of abnormal pore pressure, which includes the disequilibrium compaction, or also known as undercompaction, aquathermal expansion, clay diagenesis, osmosis, evaporite deposits, organic matter transformation, and also tectonics. There are two most common mechanisms of abnormal pore pressure, which are the compaction disequilibrium and also the fluid expansion mechanism. Firstly, we will touch on the compaction disequilibrium, or also known as the undercompaction. So, the principle behind the compaction disequilibrium is from the balance between the overburden pressure and the ability of a given formation to expel water. And in this mechanism, the formation porosity is reduced at the same time as the pore fluid is expelled when the sediments compact naturally. And the increase of the formation overburden stress is the main cause of the fluid expulsion during the burial time. And if sedimentation rate is low, the normal compaction occurs such that the equilibrium between the increasing overburden and the ability to expel fluid is maintained. So as we know, the mechanism is recognized by its higher than expected porosity at a given depth due to the less rapid decrease of the porosity. So next we will move on to the fluid expansion mechanism. So for fluid expansion mechanism, the rapid increase in the pressure of the basin and formation worldwide is due to the aquathermal expansion and also the clay diagenesis. And the overpressure in this mechanism is caused within the pore space by charging the fluid expansion mechanism, such as heating and also hydrocarbon maturation. And in this mechanism, the overpressure is due to the result of the rock matrix, which constrains the pore fluid as the fluid tries to increase in volume. And we know that this mechanism increases with the temperature and therefore the depth. Moving on to the pore pressure prediction method. So basically, there are two types of pore pressure prediction method, which is the Eaton method and also the Bowers method. So for Eaton method, it is divided into two, which is the Eaton ratio method and also the Eaton method itself. So we will start with the Eaton ratio method. It, so as we can see, this is the equation for the Eaton ratio method, whereby SV is the total vertical stress and the sigma V is the vertical effective stress, and also the PF, which is the pore fluid pressure. So the Eaton ratio method is derived from Terzaghi in 1953 from the equation which is used for soil mechanics. And the Eaton ratio method is based on the detection of change in porosity with depth. And as we know, the discrepancy which happens between the rapid formation test pressure and the predicted Eaton method pore pressure is used as an indication of the additional pressuring mechanisms for other than disequilibrium compaction. So next, we are going to talk about the Eaton method, which was founded by Eaton himself in 1972. So here we have the Eaton method equation, whereby PP is the pore pressure, SV is the total vertical stress, pH is the hydrostatic pore pressure, Vops is the observed velocity, V norm is the normal velocity, and lastly, X is the Eaton exponent. So, Eaton method estimates the pore pressure from the ratio of the acoustic travel time in the normally compacted sediment to observe the acoustic travel time. And according to Ahmed Sati in his study of a field in the southwestern Malay Basin, the Eaton exponent of 3 is usually used in sediments of under-compaction mechanism, while the higher Eaton exponent of 5 is used for deeper wells with the fluid expansion mechanism. Here we have the Bowers method, which was founded by Bowers in 1995. It is a new method which uses the effective stress approach to predict the overpressure which is generated either by undercompaction or the fluid expansion mechanism. And this method uses the concept of the Virgin curve and also the unloading curve. According to Ahmed Sati, the underpredicted high pore pressure in the deeper zones of this formation is generated due to the fluid expansion mechanism. As we can see on the right, we have two equations, which is the Virgin curve and also the unloading curve. So for Virgin curve, the V stands for velocity, and the sigma stands for the effective stress, and A and B are the Virgin curve parameters. Whereas for the unloading curve, V again stands for velocity, sigma max is the estimate of the effective stress at the onset of the unloading, whereas U is the unloading parameter and A and B again are the Virgin curve parameters. So that is all from me, and now I pass for the case study of the Northern Malay Basin to my colleague Emir. Thank you.
For case study, we taken Northern Malay Basin for our case study example. So for the geology of the study area, Malay Basin is a rapidly formed northwest southeast trending elongate reef basin located offshore Peninsular Malaysia in the Gulf of Thailand. The Malay Basin is a super deep basin containing up to 14 km of Oligocene recent sediment of predominantly terrestrial and shallow marine origin. So for the place we investigate, there are content three main lithostratigraphic interval: formation 1, 2, and 3. So for formation 2, they are divided into 5 members. They call 2A, which the oldest, 2B, 2C, 2D, and 2E, the youngest. So the overpressure analyzed with the study are almost entirely in the formation of 2B, 2C, 2A, 2B, and 2C. So formation 2A, 2B, 2C consists of shale, fine to medium grain sand, channel and crevice clay, and coal deposited within offshore data plane or data front environment. So in image here below, we can see here map of Malaysia. So this is Semenanjung. So this is our study area, the North Malay Basin. So In the zoom version here, we can see the location of normally pressured well and the well with overpressure. So basically this white dot is normal pressure well, while the black dot here is a well with overpressure. For the origin of overpressure in the Northern Malay Basin, the petrophysical properties of sequence containing overpressure differ depending whether overpressure are generated by this equilibrium compaction or fluid expansion mechanism. Compaction is impeded when overpressure are generated by this equilibrium compaction, resulting in sediment with abnormally high porosity. The other word is under compaction. This equilibrium compaction overpressure are often associated with a flow pressure increase parallel to the mean or vertical stress, and consequently an effective stress that remain constant with barrier. Unfortunately, velocity effective stress analysis cannot distinguish between the numerous fluid expansion and vertical transfer mechanism explained by Tinggi. Fluid expansion mechanism most likely to have generated overpressure in the Northern Malay Basin is the generation of natural gas, which is methane. Based on further analysis of the overpressure measurement and the regional geology of the Northern Malay Basin. While the author suggests to A, to B, and to C formation is due to fluid expansion, the vast majority of moderate and high magnitude overpressure observed is in sedimentary basin are generated by this equilibrium compaction. The primary condition necessary for generation by fluid expansion, most notably the required existence of an extremely effective seal, are also ideal for the generation of overpressure by this equilibrium compaction. There is compelling evidence that this equilibrium compaction it also plays a significant role in generating overpressure in the Northern Malay Basin. Moving on to the prediction equation. In the presence of a clear unloading signature, the Bowers equation was applied, used to fit the well data. So the equation is widely applied empirical methodology for pressure prediction. So in here we're using this equation 1. So here is the pressure profile. Well A, pressure versus depth plot. So this is the result from the case study. So the green line show prediction from the optimal modified Eaton model. So this green line here, there's a good fit between the extensive RFT pressure dataset in blue and the predicted pressure at the RFT in red. In conclusion, it is important to identify the zone of abnormal pressure in the formation. For the common mechanism, this equilibrium compaction impeded when overpressure. For fluid expansion, just gas generation through corrosion, catalysis, or oil cracking. So for the pressure prediction, we're using either these two methods, Eaton method and Bowers method.